Welcome back. We're now going to be hitting on reviewing of some graphing, specifically hitting on here these things, the Cartesian coordinate system, forms of equations, functions themselves, graphing linear functions, then actually working a little bit backwards and then talking a little bit more in detail about slope and slopes of lines. So what is the Cartesian coordinate system? Well, it goes back to this famous guy, René Descartes. He was a French philosopher, scientist, mathematician, pretty much given the naming rights, if you will. Cartesian, Descartes. So the Cartesian coordinate system is how we now currently go about graphing. And oftentimes when we talk about the Cartesian coordinate system, we're usually just talking about, just a little sloppy here, I apologize, but just an XY graph. All right, this is my Cartesian coordinate system. It's a way of mapping points on a graph. We have some specific things and names that we give this. We talk about this as being quadrant 1, this is being quadrant 2, this is being quadrant 3, and this is being quadrant 4. We say that these values on the x-axis, these are positive to the right of the central point. On the y-axis, which is the vertical axis, these are the positive values. All right, and then to the bottom side are negative for the y. To the left over here on the x, these are negatives. This is just how we define it. All right, and then that point there in the middle, we give it its own special name as the origin, as the central or originating point of a graphical system. So this is the coordinate system that we're going in. Every point that goes onto that graph has two coordinates. So if we have a point right here, that point will have both an x and a y coordinate written in alphabetical order, x comma y. And aside from the fact that I don't have any actual numbers on my graph, I know based on the fact that it's in quadrant 2 that the x coordinate will be negative, and I know the y coordinate will be positive because the positive indicating is above the x-axis. So then when we look at linear equations like this is a linear equation. How do I know it's a linear equation? If the exponent on the x and on the y are both 1, and there's no other function going on, there's no absolute value happening, I just have an x and a y, this is a linear equation. This is in standard form, ax plus by equals c, which I think is on my next slide, but I'll do it here, ax plus by equals c. So in this case, my a is 3, my b is -1, and my c is 12. But we're going to find out, are these two values solutions to that equation? To figure that out, we rewrite my equation 3x minus y equals 12. And then I'm going to take this number, which is the 0, which corresponds to, again, this is x comma y. So this is the x, this is the y. Substitute those in. 3 times 0 minus, and then the y value is just 12, equals 12. Does -12 equal 12? And the answer is not a solution. For this one, we'll go 3x minus y equals 12. Take these numbers to place them down into my equation. 3 times 1 is 3. Minus 9 equals 12. Is -6 equal to 12? The answer is not a solution. All right, so if one of these did work, then we'd say yes, indeed, it is a solution. In this case, neither of these two is a solution. What does that mean on the graph itself? It would mean that if this were a solution, which it's not, but if it were a solution, that would mean that this data point is on this line. So that's when we say, what is a solution to, is this a solution to a linear equation? We're asking, is the data point on the line itself? So there's my three types of forms that are most commonly used. This one is my standard form. This is, if you remember it, slope-intercept form. Sometimes called slope y-intercept form. very rarely, because what they do give you there is they give you the y-intercept. That's the y-intercept. M is the slope. And there's a fun, probably not accurate, but historical note about why it's called M, maybe for a later time. And this last one's called point-slope form. Point-slope form. So standard form, slope-intercept form, point-slope form. We're going to go ahead and graph these two equations. We'll start with the first equation, which is the one that we had in a previous slide, which is a linear equation. And the easiest way when it's in standard form to graph that line is to put in 0 for x and 0 for y. I use a standard t-table when I'm doing that. So I'm going to put in 0 for x, going to put 0 in for y, and see what I get for solutions on that. So if I go here, put in 0 for x. So this is 0, so I have negative 2y equals 6. Negative 2y equals 6. So my y value itself equals negative 3. So I plot the point 0, comma, negative 3. 0, comma, negative 3 is right down there. And then for the second half of this equation, for the same one, I'm going to put 0 in for the y value. So I'm going to have 3x minus 0 equals 6. Or over here, I'm going to have 3x equals 6, x equals 2. So there I have for x, the x coordinate is 2, the y coordinate is 0. So x coordinate is 2, y coordinate is 0. It goes right here. And if I can sketch a straight line, through those 2 points, that would be the equation for this line right here. To find my next one, this is not a linear equation. And how do I know it's not a linear equation? Because my exponent is on the x. We said earlier to be a linear equation, the highest power for the x and the y both had to be 1. Well, and the only power they could be as long as they're not 0. So the power on this y is 1, the power on that y is 1, the power on this x is 2, therefore this is not a linear equation. But we can go ahead and graph this anyways. In a scenario like this, it's the where do I start from? I usually throw 0 in my middle, and then I'll do like a -1, -2, 1, 2, and see where I go from there. Easiest place to start is with 0. Put 0, minus 0, minus 2. The y is -2. So 0, comma, -2 is that point there. I like working with positive numbers, so I'm going to go with the 1. So 1 squared is 1. 1 minus 1 is 0. 0 minus 2 is -2. So at 1, I'm also at -2. I then go to -2. I then put in my 2. 2 squared is 4. 4 minus 2 is 2. 2 minus 2 is 0. 0. 2 comma 0. They'll intersect at that same point. And then try -1. -1 squared is 1. 1 minus -1. Well, minus negative is positive, so 1 plus 1 is 2. 2 minus 2 is 0. So at -1, I'm at 0. So what I'm seeing here is actually I'm seeing that these two are the same, these two are the same. What's halfway in between there? Well, if I were to take the number halfway in between there, which is halfway between 0 and 1, to do a half, I would get a value that is right down here. Boop. And then, oh, got to put this in as 0. If I put in -2, I'll then have 4 minus a -2, which is plus. That's 6. 6 minus 2 is 4, so it's going up. I'm going to guess that if I do -2, I'm at 4. I'm going to guess that if I do 3, I'm going to get the same number. 9 minus 3 is 6, minus 2 is 4. And we have, if you remember this, a curved function called a parabola. But that's our quick little way of figuring out the solution, or figuring out how to graph that nonlinear equation. Getting beyond that now, when we start talking about functions, we're talking about things that are written as f of x, function, g of x, h of x, different functions with respect to x. But we can see them as respect to many other things. H of t is going to be an equation we'll see often where it's talking about the height of a function relative to time t when you plug it in. All right, a function is a mapping from one variable to the next. And in order to be considered a function, you cannot have the same y value for any given x value. So if I have f of 2 is equal to 7 and f of, let's say, negative 4 also equal to 7, that's fine. But if I have another f of 2 equals to 4, now I have one x value at 2 that has a graph, 2 points on that same graph, but the one's above the other one. So if one x value gives 2 different y values, it's not a function. All right. And then domain and range. Domain are the x values or x coordinates that are possible for a function. The range are the y values that are possible for a function. So in this graph right here, these graphs, if we look at this equation, first we say, is this a function? Well, here's the easier one. Is this one a function? The answer is no. This one's not a function. The reason why it's not a function is if I pick 0 for my x value, here's my x coordinate, so I pick 0, my graph can be either 2 or negative 2. Since there's 2 different values for that x, this is not a function. This one is a function. This one is a function. This one is a function. If you have a graph, the simple way of checking it is what's called the vertical line test, which means if I take a vertical line and I go through that graph anywhere, if I can grab just my vertical line, it's not letting me, but if I could grab just that vertical line and make it go through the graph, and if it only touches the graph once, then it is a function. If it touches twice, then it would not be a function. You can see for that ellipse that if I use that vertical line, it would go and intersect that ellipse in 2 places, therefore making it not a function. Domain are the possible x values. So for graph A up there, I look for my x values. My x values are ranging from here to there. So my domain would be from negative 3 inclusive, so bracket, not parenthesis, up to positive 5, bracket. My domain for letter B goes from negative 4 up to positive 4. Are there points at 4 and negative 4? There are, so it's bracket. If there weren't, there'd be a parenthesis. If this point down here had been an open dot for that, then this would have been a parenthesis instead of a bracket. Domain on letter C looks like it's going to go with the arrows for infinity, so this would be negative infinity to positive infinity, and here we use parentheses because infinity isn't an actual definable value, so it can't be a bracket. Okay, my range, what are the y values that I'm using? Oh, got to get the last one, sorry. My last one is the same thing, negative infinity to positive infinity. The other way to write that is all real numbers. You can use those interchangeably. Top graph, my range are all the possible y values. So I'm talking y values up and down. What's the smallest y value? Right there. So my range goes from negative 2 up to a positive 4, bracket, bracket, because it's going up to, this is the highest y value, and it does include that y value, bracket, bracket. My range on this one goes from negative 2 to positive 2. For letter C, the lowest y value is 0, and it's going up to infinity, so that'll have a parenthesis, and the range on this last one is also all real numbers. We're actually going to start over with this equation. So g of 1 means I'm going to take 1 and put it into this equation. So g of 1, so 1 squared is 1, minus 6 times 1 is 6, plus 3. So negative 5 plus 3 is negative 2. I'm going to take the equation for f of x over here. I'm going to find f of negative 2. So that means I'm going to have 3 times negative 2 plus 3. That'd be negative 6 plus 3, which is negative 3. Then we're going to do this one down here. F of g of 1 is really saying I want to take f of the g of value. So then I'm going to say I'm going to plug in 1 for the g function, which I already did up here. G of 1, we already found it was negative 2. So when you're doing it, you work your way inside out. So I do g of 1 first. So I go g of 1, which is negative 2. And then I already solved that equation. So this would be negative 3. So if I were going to be graphing this function, f of g of x, I would know that one point that's on that line, or excuse me, on that function, one solution to that function would be 1, negative 3. So what that also means, well, we'll get to there later. We're going to rewrite this one in slope-intercept form, just going back to some standard algebra practice. Remember, slope-intercept form is y equals mx plus b. We're eventually going to graph it too, but we're going to go ahead and then move everything over that's not a y, so minus 3x, negative 2y, now equals negative 3x plus 6. Then we're going to divide everything by negative 2. So y equals 3/2 x minus 3. Paying close attention to your negative symbols. Negative divided by negative is positive. Positive divided by negative is negative. Then we're going to graph this function. The reason why we like to do slope-intercept form is I can, straight from that equation, plot the point negative 3. 1, 2, 3, negative 3. There's my slope. And then I'll do this also here. Mark those off equal. This is x. This is y. And then my slope is 3/2, which means it's a rise of 3. Rise over run. 1, 2, 3. Run of 2. 1, 2. Plot my other point. Can do the same thing again. 1, 2, 3. Run of 2. 1, 2. Plot that point. And if I have the ability to, I can connect those points with a straight line. Or at least try to with my program. There it is. Going to add arrows to the ends of that equation. And that is the line 3x minus 2y equals 6, which we did in slope-intercept form as well. Last thing, slope. Slope, folks, you've done it probably a million times. Well, maybe not, but it's rise over run. It is, well, let's do another equation. y2 minus y1. The y coordinates divided by the x coordinates in order. M is equal to delta y over delta x. Get used to that because you'll start seeing more of that, especially as you get into more sciences. But that means change in y over change in x. Delta means change. And ultimately it means as you're looking at a graph, and just like we read sentences in American English language left to right, we read graphs left to right. So if I have a line on a graph that's going up, because I'm reading it from left to right, it's going up, it has a positive slope. If I have a line that's going down, it has a negative slope. Negative slope. This one here has a positive slope. If I have a graph that's going completely straight across, horizontal, it has 0 slope. And lastly, the odd duck is a vertical line. Because we're talking about rise over run, the rise in this case, if I pick any 2 points on that, the rise might be 3, but the run is 0, and you cannot divide by 0. There we go. Best of luck.